Hello everyone, welcome to the course of mathematical physics. So today we're going to show you something pretty interesting. So let me just use the special effect. Okay, why you need to learn statistics? The TAs warn me that this special effect is annoying. I know it's annoying, but it's kind of fun. So let's show that again. Yeah, statistics. So today, basically, I'm going to show you that why you need to learn statistics. So look at the pictures and also the hidden structure behind it. Okay. So here is a very ordinary picture, a natural image about the green peppers, right? And what is truly surprising is that if you treat this as an ensemble of data and analyze what the data try to tell you, then you find out there are hidden patterns behind all natural images. And so this is a very simple PCA analysis. And so then from there, you can actually find lots of interesting principal components, which is not that easy to recognize when you look at the natural images. And I think that is sort of the charm, that why I think now it is even, I know most of you are the physics students, and most of you probably do not really know the detailed techniques about statistics. But maybe it's time that you pick up these useful and powerful techniques. Let's see whether I can try to convince you or not. Taking out the quantum dynamics, we have about 4 approaches to classical dynamics. Level 1, that is, identify relevant degree of freedoms and write down the corresponding equation of motion. That we need a mathematical technique called ODE. Okay, so that's the first one. Layer number 2, this is like playing video games. In particular, I'm using OBS, so it seems that I'm introducing some interesting video games without videos. Physics research is an interesting game. And suppose if the degree of freedom somehow is divergently large. For instance, if you try to describe how the electromagnetic field changes, you need to specify you basically need to associate the degree of freedom at each special time locations. And so because of that, we then come to the field descriptions. For the field descriptions, the change can only be captured by a full set of partial derivatives. And thus, instead of getting ODE, now we get the field equation, which are typically PDE. So that's the layer number 2. So to some extent, you can think about this. If the scientific problems that you are interested in has really standing out relevant degree of freedoms, a few of degree of freedoms, ODE is the most efficient way to tackle the problems. On the other hand, if somehow you found the relevant degree of freedoms are infinite, then sometimes, or most of the times, it's more appropriate to find the field and then use the field descriptions. And thus, you would then encounter a partial differential equations. But for even more advanced scientific problems, the degree of freedoms are infinite, but somehow you are particularly interested in a subset of these degree of freedoms. And these are the open systems, okay? Open system means that you have systems actively interact with the environment, where the environment has infinite degree of freedoms. In that particular sense, the open system typically follow a stochastic dynamics. That is, it doesn't seem to have a definite trajectories. Well, that is because you ignore lots of degree of freedoms in the environment. So for this sort of problems, one of the most efficient way to solve this is in fact cook up a realistic, efficient algorithm and try to do numerical simulations. So that's pretty cute, isn't it? So you get starting from ordinary differential equation, partial differential equation, and then here you're really prompted with the challenge that you need to come up with efficient algorithms. And finally, the most advanced level is that sometimes you don't even know how you can really identify or separate the system and the environment. You were just given a set of data, and these data are not random, okay? If they are random, you can just use probability theories. They are not random. They seem to have some specific pattern behind that. So how can you then extract the information in the given data? And that's where you need the statistical skills. And typically we have conventional statistical testing methods that I'm going through, but on the other hand, this smoothly connected to machine learning, where you can also use a neural network properly trained by the data to interpret what's hidden or what's the messages that the data try to tell you. So these are the 4 different level of approaches. So let me just briefly go through how they work. So for instance, this is a typical idea that if you have a sun and then you try to find the planetary orbit behind that, you can indeed write down a relatively simple equations, right? First of all, that you just specify the accelerations from the gravitational law, but then according to definition, x will iterate by v, while v will iterate by accelerations. And just by these 5 lines, you can actually immediately obtain just the trajectories with arbitrary initial conditions. It's a very powerful. I wouldn't say that this will completely replace the analytical approach, but try to keep in mind you're not Flintstone. You do not live in Stone Age. Currently, you have access to this powerful computational machinery, and you should make good use of that. So combining analytical techniques and also numerical techniques together is truly the way to go. And also, we can try to visualize the partial differential equation. The simplest field is probably a vibrating elastic string. And we all know the field you need is that at a particular location, at a particular instant, what is the displacement from its equilibrium point? And thus, you end up with the height of or the distortions of the elastic strings depending on x and depending on t. And since partial derivatives are involved here, you end up with a partial differential equation, the PDE. And this is the very famous linear wave equation. And suppose you just give a very simple initial condition that is dy dt equals 0. That is originally the string does not move at all. And the boundary condition is fixed at the ends of the string. And suppose now just like I pull the string up here, you can actually solve it analytically and then get a solution of this form. So then you know there is a sinusoidal oscillation in space. There's also a sinusoidal oscillation in time. And this k and omega, k is quantized due to the boundary condition, and omega is related to k by the dispersion relation. But writing this up is not really the end of the story, right? If you can put this in actions, you learn more. So let's try to have a little bit of some fun. Most of you are already in your junior year, so I do hope that this sort of thing that I explained to you, that you should know the techniques. So I won't go into the technical detail. I just show that how you can actually do this. For instance, if I place the sun at the origin, and I start, and then I place the Earth initially at 1, 0. Okay, and what I'm trying to do is that I can vary the initial velocity, and then it will lead to different trajectories. Quite some fun. And for simplicity, I just choose the gravitational constant times the mass of sun equal to 1. Yes, I'm a theorist. Okay. Thus, the criterion that whether the magnitude of initial velocity is less or greater than square root 2 will lead to closed or open orbits. So I will try 4 different initial conditions. Let me explain them here. The first one is V0 equal to 1. And it ends up that the orbit is a circle. You can actually convince yourself because at that time, it just happened that this satisfies the equation of motion satisfies the circular motion. And if what happens if V is slightly less than 1 or if V is slightly larger than 1, then you got an elliptical orbit, but with different characters. And finally, if I really push the speed to 1.6, it was larger than square root 2, the total energy of the solar Earth systems then is positive. What happens there? Okay, so with the computers, then you can just read in the initial condition. So I just did that. So this is the 2-dimensional vector for x. This is the 2-dimensional vector for velocity. These are technical detail. This is a 0.001 is basically the time step that I try to generate this whole thing. And these are the total duration that I produced, generated. It's just for visual effects. And suppose now I start with the initial condition IC1, the first set of initial condition. See, it's done. The answer is there. So let me just extract these data points and then plot it out. So this is what you got. For velocity equal to 1, you just got a very nice circle here. So I hope you bear this in mind and then see how the orbit changes. Suppose now you change to IC2, which means the still perpendicular directions, but now I'm setting it with a smaller speed. Your intuition tells you that the Earth will be dragged closer to the Sun. But how? And well, visualize that, then you know how. This is how. You get an elliptical orbit like this, and notice that the Sun is now at the left focus. Okay? And also notice that this is indeed smaller than the circular orbit I just showed you before. So that is true. When the velocity is smaller, the kinetic energy decreases. Thus, the total energy remaining negative is even smaller. And so then you come closer to the Sun. On the other hand, if I boost up the speed, let's say that I change it to be 1.2, so that I would just choose initial condition 3, and for that, okay, we can now show what's the orbit that you show up. So now you know your intuition works. You should get an orbit which is basically larger, right? Because the Earth should on average be more distance from the Sun. Is that so? Well, let's try to see. That is indeed so. And you also look at this very interesting stuff. You found that when deviate from the circular orbit, for weaker bounded orbit like this, the Sun is located on the right focus of the elliptical orbit. That's cute, isn't it? And finally, if I let the speed larger than square root 2, okay, that's around 1.41 something, I'm pushing it to 1.6. So what happens there? Well, what happens there is that the total energy is positive. So the Earth is not caged by the gravitational force anymore. So what will it do? What will it do is the following. It becomes hyperbolic. That means that the orbit is now open. And so the Earth will just say goodbye to the Sun and then just fly into the deep universe without turning back. So this is something fun, isn't it? Okay, so these should be simple. And I do hope that for this sort of ODE problem, you should have the handle how to solve this. If not, you should go back to the applied mathematics and then try to integrate the analytical techniques and the numerical methods together. Otherwise, this is not complete. Okay. The second thing is about the PDE, and solving PDE, of course, is take more time. Here it's just a very cute review about what you should know about the partial differential equations. So the simplest one is the linear wave equation that I just showed you. And I said if I have a string fixed on both ends and I'm pulling it up in the shape so that it becomes a triangular shape at t equals 0. If I let it go, do you know what the wave equation will show you? Have you ever tried this before? So knowing the abstract linear superpositions and saying that, oh, okay, I'm getting the eigenstate of a Laplacian, and then I include the eigenenergy so then it starts to isolate and everything. That is not true understanding of the wave equation, isn't it? Wave typically carries information, and you would really like to see how the shape of the triangular wave at the very beginning change during this whole oscillations. You know after some time, due to symmetries, that this triangular shape will turn into the other triangular shape. But what about at other instants? Do you know? So let me try to animate the wave dynamics in later times. And this is really fun. So look at this. This is how a triangular wave will oscillate when you release it. And of course, you know how unrealistic it is. So there's a very simple, it's almost like you're just cutting this triangular shape and then to the point that the potential energy is completely gone, right? And turning into the kinetic energy and then coming to the other side. So how the wave propagates is certainly beyond your expectations. And that told you that the linear wave equation cannot be realistic. It cannot. Okay, because a realistic wave dissipates energy, and if it does not, then it would have this bizarre oscillation like this. I don't believe that in your real life, in your life, you have observed any wave oscillation, triangular wave oscillations like this. Okay. So once you have this numerical handle, you can actually educate yourself with a much deeper understanding to all scientific problems that you try to solve. So let's now go back. So what I try to convince you is that do not feel content by just write down these abstract solutions. Sometimes visualizing these solutions and dig deeper into the solutions so that you can learn much more. Because when you write this down, you don't really think, well, the answer sounds very simple and thus reasonable, right? You don't really know that it will cause a very strange shape propagations when the waves start to move. Okay? So then we come to level 3. Level 3 is more complicated. Suppose now that we are in some African fields and there are 3 species, rock, paper, and scissors. So rock would be eaten by paper, and paper would be eaten by scissors, and scissors would be eaten by rock. Basically, there is a cyclic competition between these 3 species. And how are you going to describe them? You can try to just take average, saying that, oh, I don't care. I have rock, paper, scissors. I just name them N1T, N2T, and N3T. Nice try. So then you can turn this problem into ordinary differential equation with 3 degree of freedoms. But what that means is that you are really taking the mean field theories. But remember one important thing. When two species are far apart in space or in time, they won't talk to each other. Okay, the second thing then you might know that, oh, okay, what about I just change this and then created some fields, and the field has it's called species fields. So the field has 3 values, just the rock, the paper, the Caesar. Okay, so 1, 2, 3. And then on each type, then I can say that this location is occupied by some species, and then see how they interact with each other. So this field theory description, well, it's more realistic, but not quite yet. Because if you really dig into ecologies and looking at the ecosystem, you find there are basically specific networks. For instance, even when an elephant is just very close to lions, elephants do not eat lions and lions do not eat elephants, right? So this sort of predations or ecological competition occurs on an abstract network, not really on a specific space-time structures. And thus, we need to generalize our theoretical tool on generalized networks. And so for better visualization, I just plot the 2-dimensional grid. But how are you going to describe this? Well, one of the interesting ways is that you can just cook up an algorithm, okay, to describe how they compete. And for instance, here is an RGB algorithm that we came up with. And this RGB algorithm do not require global knowledge requirement, and it's actually very realistic. And suppose now you start with the initial pattern, and you will go into a static one, but after a long time, it will evolve into what we call the pre-existing stage. And you know all the green now is surrounded by red, right? And because the green is rock, so the rock is completely surrounded by paper. So you know the paper will eat up this part, and eventually you end up something like that. And you might think the paper will win out. No, it won't. Because the paper just destroy its predators, Caesar's predator. You know what I mean? You just destroy your enemy's enemy. And so your enemies will have no fear to kill you. So at the end of the day, when paper declare victories on rock, so the rock disappear, who is the true winner? The true winner is not paper, the true winner is Caesar, because no one can eat Caesars anymore. And so the Caesar will eventually take out papers and then wipe out all the ecosystem. And for ecosystem with just one species left, no one wins, okay? It would just decompose into inorganic molecules because no creatures can live alone. Okay, so it's a pretty cute and how you can actually put a realistic evolution process on silica, on computers. And so for those who are interested in this reference game and bird things, maybe I would just explain later on. But I want to show you that using an algorithm, that is that how you pick twos. Maybe I should explain a little bit here. So how do you do this whole update from one molecular stage to the next one? That is that we use 3 different rows, reference, gamble, and birds. And so in short, we call it RGB algorithm. And of course, we particularly choose the name so that it just represented the color RGB. So how do you update? First of all, as you can see here, you put someone to gamble. Okay, and so how do you decide whether the gamble here will be annihilated or survive? You pick a reference. So in the gamble and the reference will compete. And if the gamble win over references, then nothing happened. You then return to A and then pick another reference. But suppose now if the gamble and reference, they compete and the reference wins over the gamble, then you lose the game. So the gambler is annihilated and we randomly just pick another bird, another species on the network, and then it will reproduce. So in this whole update, you need 3 references, and it's pretty interesting. You can see how this goes on, and it sort of mimics the realistic competition. You don't really compete. When you live in a society, you compete with your nearby competitors, your colleagues, your classmates, people who graduate with you within the same time frames, right? Typically. You don't really compete in very distant way, or you don't really just compete with some average, worldwide average value. That's actually not real. And that's why that we use this reference and gamble competition here. And once you lose the game, then some space is emptied, and there will be some resources left, and these resources will just give rise to some nearby. So in network with connected link, it's called nearby. It will then just pick up by nearby person, and then will just reproduce. And so with these microscopic steps, this is actually quite realistic. And then we just showed you a pretty cute simulation what we see here. So suppose you start with this randomly distributed ecologies. So there's millions of participants here with R and G and B. And since initially it's completely random, so you can sort of see these textures of how the colors distribute here. And let's see what happens when ecological competition kicks off. Immediately you start to see somehow a specific pattern is forming. It's not ordered, but there is some hidden structure here, isn't it? And so this sort of structures it's literally impossible for you to get in ODE, because if you just take average of this whole thing, you'll find N1, N2, N3 just reach some constant. It doesn't change at all. It doesn't capture this whole thing. And if you use field series, you don't really get into these long-lasting solutions. Only by multicolor simulation, you can actually see this dynamical balance between 3 different species, and their predation relation is cyclic. So let me tune it back and show you how this whole thing works. See? At the very beginning, this is completely random, but just after a few steps, you start to see characteristic length scales of L and G and B. And later on, this whole thing just evolved for a very, 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 very long time. See? I just have 2 comments here. First of all, without the appropriate algorithm, it's very, very difficult to reveal an ecological pattern like this. Second, the numerical method is just a starting point. It reveals this very interesting dynamical equilibrium, but it doesn't really tell you what's behind this. So some analytical tools from the probability theory or from the statistical theory is actually necessary to move on and deepen our understanding about this whole things. So I hope that this is sort of a really interesting features for example, for you to sort of get an idea that ODE, PDE is not really the research frontier anymore. We have a scientific problem which cannot be solved or properly approximated by ODE or PDE. And we need some new skills, and that's the multicolor simulations with stochastic dynamics. But right now, with the bloomings of machine learning, we now have even more interesting theoretical techniques that we can tackle and try to understand how the scientific world evolves. Okay, so it's time to, so the next one I'm going to show you, well, just walk you through with PCA. That's closely associated with image analysis. But before that, let me just see some questions. Oh, is this Mathematica? Yes, this is Mathematica. Mathematica is good for writing tutorial and teaching programs, but you can just choose your favorite programs. I'm not saying that Mathematica is the best program. So, okay? And is this periodic boundary condition? No. It's open boundary condition. So both ends are fixed. And so then it starts to oscillate. And in the temporal direction, in the time direction, of course, it's a periodic motion because it's a wave. And so starting from the triangular, which contain equal weight for the right moving and the left moving. And that's why when it seems to start to oscillate, you don't see anything squeezing around forwards and backwards. Great. So now let's just go back to the PCA. Ta-da! So the PCA is fun. So let me just recap a little bit more that I just showed you in previous lecture. That is single neuron with processing noise. Remember that? So you have x1 to xm as your input, and then you have y as your output. And they're related. Through a relatively simple yet important relation. That is a synthetic weight wi times xi, and then you sum it all up. So to some extent, this output y is a higher order response outputs because it integrates the input information. And in this single neuron, there's just some independent noise characterized by n. So we said we can calculate the mutual information between y and x. Remember that? And this can be done easily. So at the end of the day, we got a pretty interesting form. That is, with this relation, if we just compute the mutual information between y and x, we got basically 1/2 log the ratio of signal to noise. And so if we want to optimize, suppose the noise is inevitable, it's always there with some finite strength. So the only way that you can enhance your signal is to just increase. If you want to increase the mutual information with this log and the sigma y, so then you would just like to increase sigma y. So the question now is the following. Instead of giving this W1, W2 to Wm as parameters, now we're treating them as dynamical variable in the training period. In the training period. That is in the period that the neuron tried to learn. Learn what? Learn the message from x1 to xm. And so what would happen? Well, we go through the technical details, so I'm just going to rephrase the important consequence here. Suppose now this x1 to xm has been pre-processed, so they are independent inputs. But this xm has strongest and maximum sigma square, which means that it fluctuates most significantly, while all others are pretty much all zero. And with this input, after some trainings, you will find that this omega capital W capital M will survive with the strongest link, where all other synaptic wave will wither away and then become zero. So with these trained neurons, it then has the capability to pick up the most important inputs from x1 to xm. So that is the cute part. And this example, even though really simple, but really give us some hint, right? That means that similarly, if you just look at x1 to xm, there is just a set of random numbers. If you just look at a particular set, you don't really figure out what's going on there. But if somehow you set up a neural model or a neural network and using these signals as input to train the synaptic way, and with appropriate connections, maybe you can extract the important information from the data. So let's try to do that. Okay, so again, here is a picture. So I'm going to do something really funky. I'm going to cut these pictures into A by A, into lots of pieces with A by A pixels. That means that if you brought this up, that it's time to use this special effect again. Let me see whether it works this time. No. It doesn't work. Why? Why doesn't it work? Oh, it works. Good. That means that if you cut this, why am I using these annoying effects? That is, if you cut this whole thing into small pieces A by A like this, so then you are treating a photo as a source, as an ensemble of 64-dimensional vectors, right? Because once you cut it this way, you obtain lots of 64-dimensional vectors, something like this. x1, x2 to x6 as input. And so to draw everything simply, I just skip this very complicated single neuron with processing noise and then just write the output and then just link them up. Okay, so this is a shorthand notations of this sort of connections. So you just put in x1 to x64, and after training that this y1 will pick up the most important feature, then you project out the y1 features in the input and train the neural network again, and the second neuron will pick up the second most important feature, and so on and so forth. And then you can just keep training your data this way. At the end of the day, if you have enough time, you will train like y1 to y64. You then realize this is just some generalized, highly non-trivial transformations, right? So specifically, how do we do that? It's relatively simple. That is, if the output and the input lines up together, two neurons are active simultaneously, then you increase the synaptic way connecting them. And in order to avoid, and so in this way, either the synaptic way will stop there or will increase. But as we said, the total synaptic way should be a constant, right? So that depends on whether you just sum their absolute value together or you square them and sum it up. And if you square them and sum it up, it turns out that you need to implement an OR rule to suppress the dynamics so that this WI won't go exponential. And how can you do that? Well, it's relatively simple. You just stop this. If the Y is on too often, then you just suppress these WIs. Okay, and these OR rules can be derived rigorous, which I don't have time here, from just the conservation of the total synaptic ways. So with Hebbian learning and OR rule, you can then transform this x1 to x64 into y1 to y64. So you might be interested in how these y's look like. Yeah, so let me just plot them for you. So for the first one, the most often pattern that you got, this y, this is a 64-dimensional space. Okay, it's A by A. It's uniform. So what does that mean? That means if you cut the photos into A by A pieces, the most frequent pattern you encounter is just one color. That's something trivial, isn't it? And what is non-trivial is that the following one. For the second principal axis, the third one, you start to see one node. For the fourth one, there seems to be two nodes, and then more and more nodal lines. So these are really something surprising because if you just look at the original pictures, where does these features hinted? You cannot really read it out from your eyes, and if you just use ordinary modelings, it's very hard to find what is the specific features behind us. And so, inspired by these hierarchies, I'm going to just dump most of the information. For instance, here, after doing the PCA, I know what are the important information, what are the less important information, right? So then I only keep 20% of the original visual data, and this is after PCA compression. This is the original image, and try to take a good look at these two pictures. You can barely see the difference, isn't it? So this is significant. That means that most of the natural image only contain very, very few precious visual information for your eyes. Okay, and why is that? And there's a huge mysteries behind this whole thing. And hopefully, at the very end, when we learn all the basic statistics techniques, then I will come back to PCA and then sort of show you that how this works. So I guess that here I just want to emphasize one important thing, that once you sort of know how to look at this whole thing, something changed, right? You just look at a photo. If I didn't show you this, would you ever think about a photo? It turns out to be a reservoir, an ensemble of 64 dimensions. And would you ever think about that this 64-dimensional vector do share some specific features behind us? And I think that is the powerful part in modern times, that there are more and more algorithms and different ways to analyze different sort of data. So then we now have a completely different understanding about the data that we collect before. So it's not just about using some simple model to fit the data. It's quite the opposite. That we use the data to train a specific neuron structures and then try to extract the useful information as the outcomes. So this is a completely different logic than previous ones. So let me go back to this important slide here. So in fact, personally, I think this is probably the most important things that I try to pass on today. That is that for scientific problems without quantum flavors, there are 4 layers of approaches. The first one is ODE, the second one is PDE, and then you come with how you deal with stochastic dynamics. And smart you might then notice that why I choose the specific topic of mathematics physics this semester this way. The stochastic dynamics, what is the driving theory behind this whole thing? That's probability. And finally, sometimes we don't even know the probability distribution. We just have the data. So there are several ways that one can do that. The classical ways in statistics is that then try to guess what the underlying probability distribution is. And this is what we call the maximum likelihood method. That is that when you are given a set of data, then you try to see that what kind of stochastic dynamics will maximally likely to generate the major result. And these sort of things really come to the level for these are the statistical problems which can only be solved by data analysis. And machine learning is one of the most powerful tools nowadays to solve many challenging problems in data science. Okay, so let me take eta is the learning rate. Why call the image pixel as an ensemble? Okay, so let me go back. This is the crazy one that here, this is the photo, right? So I cut it into many 8x8 pieces. So each piece contains 64 grayscale information, right? But since you have lots of them, so then you assume that behind it, there is some probability distribution of this 64 dimensional vectors. And thus, by cutting a photo into this, you make an ensemble, right? Because you just, you sort of, oh, this is the first samples in the ensemble, the second one, the third one, and the fourth one. So it's really cute. You're treating a photo as a consequence, as an ensemble of 64 dimensional vectors. That's what I mean. So this is certainly not familiar, okay? And so the second one is the eta is the learning rate. Yes, eta is the learning rate. That's the simple one. And we got this for RGB gambling example. Can one write down the nonlinear diffusion equation to describe the process? Also, how can one find more references regarding this example? Okay, okie This is actually a paper that I finished with my PhD student, who is now applying a similar spirit of algorithm to prevent or to control the pandemic damages in the whole world. So how can you find more references? Let me see. We're going to publish this paper soon today, so then I can give you the references. Sorry about that. And the second one is that can one write down the nonlinear diffusion equations to describe the process? The answer is yes, you can. But since typically the algorithm will lead to highly nonlinear ordinary differential equations. So once you taking some approximation, then going down there, you got something which got smoothened out, and sometimes it got completely different result. So, but since we can generate this just by algorithm to the precision that we would like to do, it's sort of just making that, you know, so then one can just give up your security blanket that previously, think about that, before the computer eras, when we talk about analytic solutions, we always talk about fundamental equation, the power series, and everything. But what if for some other solution which you don't really have this analytical form? Are they less important? No, they are not. It's just that they cannot be described by the tool that you are familiar with. So I believe that for this RGB algorithm, there would be some equivalent nonlinear diffusion equation with stochastic noise and also highly nonlinear interaction between them. But can the coupled nonlinear diffusion equation recover the result? Probably not, because the species here are discrete. And they're also what we call the neutral drift due to the finite population and all sort of things. And all these are not very easily captured by diffusion equation. So this is a very deep one. Okay, great. Nice to have so many questions along the way. So finally, with that 4th level skill in mind, and I hope now you're more interested in learning the statistics. So unlike probability, so if you look at the probability and statistics, this is sort of the cause and there's a causality between those. Suppose now you know the probability distribution function. You can just use a generator to generate lots of data, right? Random data. So, and in statistics, the question is the opposite. Typically, is the opposite. Is that you are giving a lot of data and asking, can you reconstruct the underlying probability distributions? Or can you tell me this, if I have a hypothesis that this is generated by some Gaussian distribution with specific mean and specific variance, sigma squared, is this right? Can you give me some confidence level that whether this hypothesis is correct or not? And that would be almost like the inverse problems as compared with the probability series. Okay, so here we are going to introduce these concepts step by step. And rightly, even though the chapter is not particularly long, but I believe that it's literally impossible for us to cover all these materials within 4 lectures. So let me try to just pick the most important one and thread them through with reasonable logic, and I do hope that you learn to appreciate the beauty of statistics. So we'll start with the first concept. That's what we call random sample. So what is a random sample? Think about that. Random sample means that you have some random variable x, okay? And you just measure it n times, so you have x1, x2 to xn. Okay, so how are you going to describe the outcome of x1 to xn? Well, you can use the joint probability density functions, the probability density function x1, x2 to xn. This is really nice, okay? Nice things in probability theory is useless. And so you write out a very complicated joint PDF. Yes, but how are you going to deal with that? So typically, we will introduce the independent measurement assumption, saying that each measurements are independent to each other. That is, the outcome of x1 does not depend on x2, and the outcome of x2 does not depend on x3. And for curious cat, really, this x1, this 1, 2, 3 to n labels really mean something for physicists, because this 1, 2, 3 to n just mean T1, T2, T3, and Tn. And if you really then go back to the Markov chain that we explained before, then you found this independent measurement assumption is a huge one. It's truly a huge one. So for some particular questions it works, but for some others it does not. So please be careful. Suppose now we introduce the independent measurement approximation, so then this joint PDF can be written as a product of different PDF. So for x1, it follows a particular PDF. For the x2, it follows another PDF. PDF is a probability density function. And for the Pn, it just follows a Pn PDF. And they may not be the same. Furthermore, I'm going to just assume that I'm drawing these samples from the same population, or I'm saying that all these probability distribution are the same. And thus, finally, this can be written this way. And once you approximate, this joint PDF can be decomposed as the repeated products of the same PDF for just one random variable x. And the outcome of this x1 to xn is called a random sample. That said, let me just give you a trivial example. Suppose now you have a dice with 1 to 6 points, right? And if you just roll the dice n times, then you will get a set of x1 equal to like 1 or 2 or 6 or 1 or 3, and the collection of this is just a random sample of the dice. So that's relatively simple. Okay, once you get these samples, you can ask what kind of statistic you can do So here we're going to introduce several important sample statistics. And this is also the part that I struggle a lot, because I know that we use the Riley as the textbook, right? And so it's published by Cambridge University Press. Supposedly it should be good. But then Riley here used a very rare convention for population and the sample means and variance. If I follow Riley's convention, then of course then I follow the textbook, then you would actually find difficult time to understand all other papers in the whole world. And so then I decided that I would just follow the mainstream, the usual conventions. So from now on, you will find the content that I try to introduce to you still pretty much follow the same logic as presented in Riley, but in terms of detailed formula, you might find them different. Okay. So first of all, suppose now you only know the data x1, x2 to xn. So the first thing you can do is do the sample means. So this is trivial, right? This x bar is 1 over n, sum I from 1 to n, xi. That's great. The second one is that you can do an unbiased sample variance. And the unbiased sometimes is ignored and it's just called sample variance. And so instead of divided by n, here you divide it by 1 over n minus 1. And this is really a very famous one that we will explain in our next videos, the statistical estimator. So don't miss that. I will explain why these Bessel corrections occurs. And that is actually a very important concept, that how you go from sample statistics to estimate how good the probability distribution function is. So just trust me and just trust me that here, instead of using 1 over n, we're using 1 over n minus 1. This 1 over n minus 1 sounds a little bit weird. And what we are going to do is that we use this x1 to xn, we calculate x bar first, right? So then we start to calculate deviation around the sample means. And I squared it. And if I just divide it by n, that seems to be the variance, the definition of variance we're more familiar with. But it turns out if you do that, this sample variance you define it this way is biased. And somehow Riley choose to define it this way and then correct it to get the Bessel's corrections from time to time with different notation. I just find it very, very hard. If I teach you this way, you might have a really difficult time to align with other important results written in other textbooks. Okay, so the sample variance, keep that in mind. There is a mysterious 1 over n minus 1 factor. And so that's relatively simple. So here, not only just the algebraic means that we can define, there are also different sample means that one can define. For instance, you can define the geometrical means. You just multiply them together and then take a 1 over square root. Or you can sum up the reciprocal, everything, take average of it, and then take the reciprocal. Or you can square them and sum it up and take the average and then take a square root, and that's the root mean square. So there are different sample means that you can take. So which one is the correct one? And this really reminds me that several years back, that during a chat that I talked to my collaborators on what we call the resisted RAM, RRAM. And the resisted RAM is a multi-layer structure like that. You have nickel oxide and you have platinum, and nickel oxide is insulating, and you try to pass through some current pulse, and you find something truly interesting. You find originally without any treatment that this R0 is relatively small, but then if you then send in a current pulse, this resistance just jump 1 decade up. That means 10 times. And if you just send in a sequence of 4 voltage pulse, then it jump up to 10,000. That is 10 to the order 4. And because the resistivity changed so much, okay, you can actually use these resistive states as a memory storage, right? Because you can just control how many voltage pulse you comes in, and then you would be sitting in different resistive state. And this is really great because this is R0, this is like 10 R0, and if you send in 2, you're about 100 R0, and this is like 10,000 R0. And try to remember, I'm not talking about like 1 ohm, 2 ohm, 3 ohm differences. I'm talking about 1 ohm, 10 ohm, 10,000 ohm. Okay, it's a logarithmic. It's an exponential differences between these states, and thus fluctuation can be largely ignored. And in fact, this is one of the very powerful candidates to replace the DRAM that we are using right now. So what's the puzzle? Well, the puzzle is that at that time, well, first of all, let me claim, I'm not an expert in RMs, okay? But just during a chat, they told me that they have lots of resistance data, X1, X2, X3, and Xn. They tried to analyze it, but they couldn't find a pattern. Then it reminded me, aha, maybe you can choose a different means, right? Like in the pandemic area, everyone is very familiar with the PCR values, and suppose now if you like measure the PCR value, you get different, like the first time you get X1, X2, and X3, and all sort of things. Which means do you need to use? And after some analysis, it turns out you should use the geometric means. Okay, and we also know when you try to study the velocity or the speed distributions in a gas, in an ideal gas, the root mean squares is the right velocities to use. Okay, so what about the RM? It turns out the harmonic means is the right one to use. So we use that. So instead of using resistance, I reverse that. Okay, I reverse that, compute the average and reverse it again. And then plotting it, and it found that just with a very simple binary resistance model, that is that this whole RM is composed of lower resistance segment and higher resistance segment. That means that each segment is just like the Ising model, is either pointing up or pointing down, corresponding to little r and capital R. And you calculate how this distribution lead to eventually sum of the overall resistance. And it works. The series and the data match rather nicely. And as you can see here, instead of using resistance, you use conductance. Okay, and so this is 1, and this is like 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and if you further set it, then it got into the most insulating states. Okay, so I won't dig into the detail, but I just want to show you that when you have some sort of data, sometimes you need to sit back and ask yourself that what kind of means that should you use to really deposit yourself or to unveil the statistical puzzles in front of you. And sometimes it's not just the ordinary means. Okay, and if you're interested, this is a published result that in Nature Publishing Group, Asia Materials, back in 2014. So it's quite a lot. It's about 8 years ago. So what is the true takeaways? Haha. The true takeaway is the following, that I noticed that in an RM there are many parallel conducting channels. So after some analysis, I realized that choosing resistance Xi is bad. You should choose conductance Yi, which is the reciprocals. And then you now know if you choose the conductance, you can just calculate the ordinary conductance and everything will just work out fine. So don't worry that in the textbook you might encounter saying that, wow, their geometric mean, their harmonic means, their root mean square. What about the variance? So we'll have geometric variance, harmonic variance, and root mean square variance. In principle, yes, we do have this, but in order not to confuse ourselves, typically we don't do that, because that makes the technical detail rather hard to follow. So going back to the statistic, that do not directly jump into all these sample statistics. Ask yourself, do you really find the right random variable to start with? For instance, the question I ask myself at that time is that, is the resistance the right data to use, or I should convert it and then analyze the conductance data? It turns out if I just choose the conductance as the data, I can just use the ordinary statistical tools without any problems. So now, with this in mind, can we reinterpret the geometric mean or the root mean square means? The answer is yes, we can. When would you come up with this, that you need to multiply all your data together and take a 1 over n square root? If you analyze the stock market, you realize that you need this. Okay? And so that is because the outcome is coming from a product of, it's an end product of lots of previous results. And so whenever you need to use this geometric mean, typically that just means that this x is not the natural variables that you should choose. You should just choose log. And if you choose log, then you realize that this geometric mean is nothing but the ordinary algebraic means of yi's. So what about the root mean square? For the root mean square, that is also simple. For the root mean square, it just means that the correct random variable is not x, it's the x squared. Okay. And with this in mind, now you probably know that, log, reciprocal, or the square, of course, is not the only function you know. So you have lots of functional form that you can try to basically redefine your random variables. And in the redefined random variables, usually the statistical sampling will become much easier to capture. Okay? So here, and in fact, in the ideal case, you probably know that why this yi is better, because this vi is the speed or the velocity. The square of it is the kinetic energy, and we all know the energy is the central role in Boltzmann distribution, and that's why that this y is a much better choice when you try to analyze the problems. Okay, so I guess, wow, we are really running late. But since it's an online course, let me just torture you a little bit. Sorry about that. Sorry. And so finally, promise, we'll talk about the sample covariance and correlations. And if, for instance, right now I have two sets of random variables, x and y, and I plot them together. This is really intuitive. If you plot it like this one, then we said that they are not correlated, right? And if you plot it out and you find this x and y follow the distribution look like this, that means they are positively correlated. And on the other hand, if you find that when x is bigger, y is smaller, when x is smaller, y is bigger, then that means that they are negatively correlated. Okay, so this is positively correlated, this is negatively correlated. So this inspires us. Maybe there is a way that we can calculate the correlation from two random variables. They are not independent, and because the visual effect is just so obvious, you probably know that this shouldn't be that difficult. And it turns out the math is relatively simple. Again, I'm using the sample variance and the sample correlation, slightly different from the one introduced in the textbook. So for the sample variance is again defined with the Bessel's correction. And thus, when you simplify this expression, you really need to be careful, okay? Because this x bar contains 1 over n, not 1 over n plus 1. So then all the identity and the relation used in writing may not work here. But I'm really using the most commonly seen conventional notation. I apologize one more time that I didn't notice that Riley chooses a rather different convention than most textbooks. But I look up other statistical textbooks, and so I decided to follow the conventional wisdom. So the sample variance of Vxy is 1 over n minus 1, xi minus x bar, and yi minus y bar. Okay, so this looks very much similar to how we define the covariance, except when you're talking about sample covariance, instead of divided by n, you divide it by n minus 1. So what is sample correlation? Well, simple, because we have defined sample variance and also sample covariance. We just divide the sample covariance, and this Sx is square root of the sample variance of x, and the Sy is a square root of the sample variance of y. Remember that? So it should be somewhere here. Okay, remember this. If I take a square root of this, so all the expression will be extremely ugly here. And that's why for statistics, it's actually better to try to write reports instead of really put you into the written exams. And by doing so, try to remember that all these variants are with this 1 over n Bessel corrections. And so then it's straightforward to show that the sample correlations is between 1 and minus 1. For 1, it's basically x and y are positively correlated. For minus 1, that just means they are negatively correlated. And this gives you a pretty nice visual cube. And because of this, you also notice when you are provided with some set of data, if they are truly not correlated, okay, so all the data scatter around, theoretically this is actually not very hard to handle, because in 2 dimensions you might think there is no patterns and sort of thing, but well, since they are not correlated, so what can you do? You can reduce the problems into 2 much simpler questions. Yes, you need to solve x and y problems, but since they are all simple, so you will be fine. Okay, so this is actually not the challenging one. For this, you also realize that x and y are no longer the good choice, because along this is where the variance become the largest, right? So if you, for instance, in this particular case, if you just choose x plus y as your random variables, then you will find that its complementary part x minus y is almost 0, right? It's a very small fluctuations. And thus, that means that when 2 random variables are strongly correlated, and if you really know how they are correlated, you can actually reduce the data dimension. And that's the trick that I have played for you in the photo that I showed you. So in this trivial case, you already see that, aha, I know along this direction is the most important direction. But if I give you a photo, then it might not be that trivial, right? And that's why that learning some basic techniques of statistics will help you to see the hidden features in the given data. Okay, so sorry for running late. I guess that would be all that I would like to see. And this is really something Q result. Let me stop here. And I got some question one more time. Oh, this is in Mandarin. 在电阻的时候可以换成 1 over x， 算气体的时候可以用 RMS。请问一下老师，什么物理系统用 geometric mean 取 log？ 呀，这个其实事实上是还蛮单纯的。物理的话就很难讲，但化学其实常常做这件事。像我们在做萃取的时候，那你萃取的多纯多不纯有没有？这跟上一次是有关的。那你如果用一个比例去做，你最后其实就会得出一个几何级数。在这种一个状态底下，那 PCR 其实就是这样做的。在这种状态底下，你就会用 geometric mean， 也就是说，因为它们其实是相乘的。其实你如果每一个，你不要去。就是说我们比如说像声音为什么用 decibel， 就是因为我们取了 log， 所以我们如果浓度都取了 log 之后，它们其实上就是加减乘除的关系，于是你就可以把它恢复成很正常。那有另外一种互相这样跑过来，比如说像我们今天在研究一个族群的 fluctuation 的时候，你如果直接用族群，也发现其实上不是很好用。为什么？因为族群在生的时候，就是多的就会生多嘛，少就会生少，也是在一定程度上它是用比例去生的，对不对？所以像这种用比例去生，你最后其实上也是一大串的东西要乘在一起。那在这个时候，你如果取 log 再去分析它们，你也会发现，其实事实上整个数据会变得比较简单。那还有另外一件事情，在经济学上的时候，比如说今天股票涨或跌，那是看原来的基数是多少嘛。去乘上一个比例涨，一个比例跌，所以如果你直接去分那个股票的涨跌的话，你会发现超困难的。但你其实应该要把股票怎样，股票指数乘 log， 你再去分析它，你就会发现它其实事实上遵循一个还蛮漂亮的一个 bias 的 log 的Gaussian这样。So 那如果你今天用原始的指数，我们就说这个叫 log normal。但如果你今天先取了 log， 它其实就是 normal distribution 哦。所以像这一些的话，其实都还蛮常用。不过在物理里面，什么时候会用到这个呢？如果是说真的是说物理，那我想想看好了。对，所以我刚刚其实已经举了3个，无论是萃取像 PCR， 或者是说在演化上面族群的整个浮动，或者是说在经济学上股票指数，这些都是我们会用到 geometric means， 很棒很棒的问题。那我觉得大家其实在学这些统计的技巧的时候，真的不要忘记了，其实要把它运用到实际的问题去，才真的是有用。不然你学这些东西第一，其实我几乎可以跟你保证，你一定学不全因为这些东西都太抽象了，你会学得很辛苦。所以试着去提这样的一个问题，那我会把我过去的一些经验也跟大家分享好吧？那很感谢。那今天因为时间已经拖到有点晚了，所以呢，我想我们今天就直播到这边结束咯。谢谢大家今天跟着我在这样的下雨天，非常有上课的氛围。那不要忘记了，待会3点钟的时候，要上 Zoom 的线上会议室，我们要讨论一下期末报告的事情。好，